All right. So the last bit in this class is the idea of instantaneous center of rotation. And to see that, for now, we only look at, let's consider only planar motion. So if I have a rigid body, something like this, planar motion means path of all points in the body are always parallel. Parallel to a fixed plane. Okay, that's better. So if I have all the bodies, each one of them moves, and I track the path of all points, all of them remain in the same plane that are all parallel to a fixed plane. That is what we call a planar motion. So for now, let's consider this, and 2 points on the body. So this is point A, moving velocity VA at this time, and I have this point B moving at velocity VB. So in planar motion of a rigid body, so this is, let's put it here. I have in planar motion of a rigid body, both of these are important, planar motion and rigid body. Always there exists a unique axis or point axis about which the body appears to be rotating. There exists a unique axis. Let's put it at any instance. There exists a unique axis about which the body appears to be rotating. And this unique is, well, let me see. Both of these, there exist, and unique in, it is possible that that point could be at infinity in the case of just a translation, but that is just a generalization of the same statement. So this point or axis, let's call it a point, is called instantaneous center of rotation, and it has the only point with v equals 0. Well, if the whole body doesn't move, yes, all points are essentially instantaneous center of rotation, and all of them have 0 position. But if the body moves, that instantaneous center of rotation or center of 0 velocity is the only one that has 0 velocity. So IC and V of IC is 0. this instantaneous center. It is a very useful kind of concept, and that can simplify the solutions usually very much. And for instance, if you know the velocities of 2 points, we know that if the body is rotating about a fixed point, the velocity should be perpendicular to the line connecting them to that center, and by forming the perpendicular where they intersect is instantaneous center of rotation. And from here you can find out that the rate omega, let me change color. The rate of instantaneous rate of angular velocity, instantaneous angular velocity, omega is this VA divided by rho A, the distance to that point, equals VB over rho B. And if I'm interested to know the velocity at any other point P, I can connect that, and VP, in this case, VP is this same omega times rho of P, or maybe in a vector form. Let's put it this way. V is this. If I know the vector, omega cross rho P. Okay, it is very useful concept, and that can simplify the calculations often significantly. A couple of notes. Note 1. V of IC is 0, but acceleration of IC is usually not 0, usually, in most cases. And that is the good example is a wheel. Oh, that's not a good wheel. Ooh, I'm going to struggle drawing this. I have the wheel. So at the contact point, this V at this point is 0, and that is the center of rotation. But this point is just a point on the wheel. So before the wheel is rotating this way. So before this point was here, and after it's going to go there. So essentially the point, if I look at the path of the point on space, it's going to follow such a path, and obviously it's going on a curved path, and it has an upward acceleration. That brings me to note number 2, that V of IC is 0, but trajectories of ICs, pay attention to this plural, may have a velocity. And again, looking at this, so right now this point has 0 velocity. Before another point number 2, so let me maybe color code them. This point is this point, is that point. This point that is Now center of rotation is a different one. And let's see, yellow. If where is it? Where did it go? Oh, it's such a bad color. Let's see. Oh, I made a mistake. What color? Let's try. Oh, I'm struggling. Okay. And in near future, this point will be center of rotation. So these are different points that will momentarily become center of rotation and then have velocity again. But the trajectory of them has this velocity v, which is not zero. And we know that it's r omega. It has that velocity. So it is important to know the difference between the trajectory of ICs, or the locations or loci of ICs, and the velocity of a single IC itself. And the last maybe note, not a note or something similar to that. Note 3. This is valid IC. Exists in planar motion. In 3D motion, we do not have that. We don't necessarily have that concept. IC does not necessarily exist. Instead, what we have is a instantaneous. We have how do you write instantaneous? Instantaneous screw axis. Instantaneous screw axis. And that is easy to figure out why we need that concept. So a screw axis is an axis that the body rotates about and at the same time move along that direction. And you can think of really a screw that is rotating and moving up. So you cannot find any point on that body that has zero velocity, but the points that are along the axis have strictly velocities in the same direction as the screw axis. So that is kind of the extension of the concept in 3D. All right, now we have covered a lot of concept in kinematics of objects, kinematics of particles in 3D mostly in these 3 or 4 lectures. What we do next is use these kinematics and try to solve the dynamics of the bodies. So F equals ma. So until then, happy studying.